My name is Patrick, and yeah, I'm a PhD candidate with Dr. Travis Esau, and my work deals a lot with machine vision and artificial intelligence, and trying to do some things in the cropping system with that. Uh, a bulk of the research works on using that to develop a machine vision-based sprayer to help reduce our herbicide application use. So what I use is an algorithm called a convolutional neural network. This is a form of artificial intelligence that's really good at analyzing images. It got started in the 90s in ATMs. When you put a check in the ATM, it can read what numbers are on it. It's using the same technology. And what we're doing is repurposing the technology in larger form to identify weeds in wild blueberry fields, namely hair fescue and what you see on the screen now, sheep sorrel and other weeds. We can identify these with a high degree of accuracy with the algorithms we have available to us today. And what this is really is just a form of artificial intelligence. So mathematicians and psychologists in the 1950s created this mathematical model of how animal neurons work and then programmed them into a computer. Now, in the 1950s, there wasn't a whole lot of processing power. So the idea didn't go anywhere very quickly. But with today's technology available, we're able to create these artificial brains in software with millions of these artificial neurons to allow us to do these identification tasks. So with the precision sprayer, what we've done is we've taken these algorithms, we've trained it to identify weeds, and then using images, we can then pick out our hair fescue or our sheep sorrel or our goldenrod, and then with cameras pointed directly towards the ground, have it so those spray nozzles open when there's a weed right there and keep them closed otherwise. So to do this, we need a few pieces of hardware. First, we need a camera that can actually take those pictures at high speed, and then something that can process those images with our convolutional neural network, or CNN, to see where those weeds are. We also need some nozzles that we can electrically actuate on and off based on what the camera sees, a controller for those nozzles to take the camera input to translate that to something the nozzle understands, as well as communication lines to wire everything together. And all of that has to work in real time. So the camera we selected for using this is called the Oak D. D stands for depth. It's actually a 3D camera, but we're only using the 2D functions built into it. We bought these at the height of the COVID electronics shortage, and the supply chain for the 3D version was just better. Everything that I show you today can be done with a simple 2D RGB camera, similar to the ones that we find in our cell phones. What's neat about this camera, though, is it has the neural network processor built right into it. So it captures the picture and it runs the AI algorithm and sees where the weeds are and then sends that back to the computer rather than the whole image, which makes things happen a lot faster. And what it does is it captures that picture and then it scales it down to a smaller size. And when we have these small size images, it takes a lot less compute power to analyze them. So I load my algorithm on and it processes the images at 52 frames per second. It can capture and analyze and pick out weeds 52 times every second, and then send that information back to the tractor to control the nozzles. Now, the cameras don't operate by themselves. They need something that is going to tell it which algorithm to run and when to run it, and then what to do with those commands. So for instance, we need to be able to tell it, detect hair fescue, detect goldenrod, or, I have one that works on clay pigeons because I'm not always testing in blueberry fields, especially when the ground is covered in snow, which I'll get into more of that later on today. So we use this single board computer called an NVIDIA Jetson. It's about the size of a credit card. And all it does for us is it loads the appropriate neural network onto the camera for processing, and then sends the information from the camera back to our computers further down the line. For our actuating nozzles, we worked with Pentair and their subsidiary HiPro to use these nozzles that actuate on the isobus system. So isobus wiring communication system, it's a tried and true method for hooking up implements to tractors in the electronic sense. So in the lower picture, what you see is a screen where essentially you can press a button on the display in your cab and turn a nozzle off and on with touch input. Their system also supports loading prescription maps. So if you know where your weeds are already, you can just load your prescription map in and the nozzles will apply where they should. Uh, with our system, though, we're using that vision-based input, and Pentair was really good about giving us all the documentation that we needed to program into their nozzles. And not just us. Anyone with the electrical engineering background can download the documentation right from their websites and make their own system that works on this technology or anything you want, really. You could have your own display. If you're really creative, you could have a piano in your cab with one key to actuate every nozzle. Not practical, but absolutely doable with this system. So to actually interface with that, we do need a box to translate my camera inputs into something that works on Isobus. We worked with another lab on campus, the Applied Intelligent Engineering Systems Lab, who have some really talented electrical engineers to develop this device, and it worked really well. And now that some of their members have moved on and graduated, this year we actually built a new one in-house in our lab, which allows us to streamline development a lot more quickly, add new features, and make things faster and more stable in a quick fashion. So when we lay this all out, we have one camera for every two nozzles. So we have the camera spaced about every 40 inches with a 20-inch nozzle spacing. In the video we showed earlier of the weed detection, you can see it draws boxes around where it sees the hair fescue tufts or the sheep sorrel leaves. So depending on where those weeds are in the image, it can actuate one nozzle or the other to spray the appropriate location to hit those weeds. We wire 3 cameras into a single computer over USB. The reason we don't do more is 2 reasons. 1, power limitations of the computers for powering those cameras, and 2, it's the length of wires you can actually run with USB. The spec is about 15 feet, and most sprayers are going to be wider than 15 feet. So we have to use multiple computers to wire up these cameras. Now, as far as connecting everything together, we use Ethernet cables, network cables for your computer, the same type that you would use to plug your home computer into your internet router. Those can run for about 200 feet without any problems. So we have internet cables outdoor rated running along the boom of the sprayer to connect everything together. And we set up a local internet network on the tractor, which allows all the computers to communicate, including this MVN that will translate all these commands into something the nozzles can understand. So our final solution here is a retrofit kit that works on existing commercial sprayers. The one that we're using on campus is an MS Gregson P1135E. It has 27 nozzles spaced at 20 inches apart. We're using Hypro's ultra-low drift nozzles to help with, well, preventing drift for our spot application. When we were testing, we ran it at a system pressure of 50 psi and drove over our target plots and weeds at 3 miles per hour when we were spraying. We have those cameras spread along the boom, one for every 2 nozzles, with our artificial intelligence algorithm loaded onto it. Now, it might be a little bit difficult to see in our on the right-hand image there, but those hair fescue tufts all have a percentage next to their label. 47%, 86%, and so on. The thing about artificial intelligence is that it's inherently guessing every time. It's just probability. So when we're setting up this system, we have to decide what's the probability threshold that we want to spray at. The default recommendation is 50%. If it's 50% certain that you have a target, it's a true positive. Due to a lot of factors like the fact that we're moving and there's a lot of shadows, I found that lowering it to 40% was often a good idea to make sure we get all the hair fescue. But we'll dig more into that data in a minute once I show you my results. So when we were testing, we tested really during 2 time periods of the year. For a pre-emergent application in spring of the sprout year, and then post-mowing in the crop year in the fall. Our test tracks were between 80 and 120 meters, just depending on field geometry and size and where the weeds were that we were targeting, where we could see them. So we put down water sensitive papers in every test track, 8 in locations with hair fescue, 8 in locations without hair fescue. And then we looked at how many true positives we had, how many false positives, how many false negatives, and calculated precision and recall as our 2 evaluation metrics to see really how the sprayer is doing. Is it picking up what we want it to, and is it avoiding what we don't want it to spray? Now you'll see in the image here, the hair fescue is pretty green, and that's true with a lot of the images in our training data set. To train the AI, we gave it roughly 4,000 pictures of hair fescue, all labeled with those bounding boxes so it could learn what hair fescue was. Now the difference is different times of year, the hair fescue is not always going to be green. So it makes kind of a challenging thing to consider when we're looking at different growth stages of the plant cycle. And last year when I presented, I was really excited about how the progress went in May the previous year because we were hitting more than 90% of the hair fescue. The issue I saw, though, is when I took it out last December, after our meeting last year, I was only hitting 63.6% of the hair fescue. But don't worry, I'm still in a good mood. We managed to fix it. So that picture you see with that nice green hair fescue was captured in May. In December, it did not look like that. It was brown. And I thought that might have been the issue. And it might have been part of it. But we went back out a couple days after our testing, and rather than spraying, just took pictures. I knew the algorithm should be able to detect brown hair fescue because I did include that in the training data set. So we decided to try it again. Went back out, and the images were all really blurry in December. A lot blurrier than what we got in May. And the reason for that is actually how cameras capture pictures. So when you take a picture on basically any digital camera, including the ones that we all carry in our pockets and our phones, there's a sensor inside. And the exposure time is how long the sensor is exposed to light to capture that digital image. Have you ever tried to take a picture of someone while they're walking or running and it comes out blurry because you're moving? They're moving while you're taking the picture? This is why. Your exposure time, if it's too long, that object is going to smear across the screen. And that was what was happening in December, but not May. The thing is, it's darker in December. Our eyes and brains manage to account for that automatically, so we might not notice it as much. But if you take a picture with the same camera settings in those 2 different times of year, it's going to come out darker in December. And what happens is that exposure time increases to account for that, so you can still get a nice bright image. With a longer exposure time, it creates a really blurry image. So we couldn't actually see the hair fescue because it was just a blurry mess in December. So I had to figure out what sort of exposure times can we use in December to make sure this works properly. Now, by the time I figured this all out, it was about February. So the hair fescue's covered, covered in snow. So what we did is we trained another neural network to detect these clay pigeons. We put one of my cameras on our ATV in the lab, and we took some light readings, and then we drove over these clay targets. We did it at 3 and 6 miles an hour, as well as just taking still images with these cameras. I tested exposure times of 5, 10, and 15 milliseconds and 30 milliseconds, which is the maximum amount of time that this camera will set the auto exposure at, just to see, what does that do with blur? What does it do with lighting? We tried different processing resolutions. Like I mentioned, we usually downsample the images before we process them. And we tried boosting the color after using gain or ISO. We use this algorithm called the variance of Laplacian method. So we essentially multiply the pixel values in the image by that matrix, and it gives us a number. Higher number, sharper image. And then we compared that all with statistical methods, factorial design. And most of the effects were significant there. But the interesting part here is what's in the chart. So that top row is what images look like when they're still at these indoor lighting conditions at these different exposure times. So you can see at 5 milliseconds, it's a pretty dark picture. And at 30 milliseconds, it's brighter, and 10 and 15 are, somewhere in the middle. But as we start moving, if we have that 30 millisecond exposure time, at 3 and 6 miles per hour, that target gets really blurry and really messy looking. It's hard to identify some of the features that you can identify when it's still. So ultimately, I decided to drop the maximum exposure down to 5 milliseconds and try this system again. So this helped a lot. Um, the first two rows of this table are the two rows that I showed you previously. Uh, poor results in December. Uh, but then, we went back out in May. We put the limiter on, even though we weren't sure that we needed it. And instead of hitting 90% of the hair fescue, we hit 100% of the hair fescue. It picked out every tuft that we had water sensitive paper on. And, we still ended up missing a lot of the blueberries. Uh, but I figured if we can hit, 100% of the hair fescue, why don't we try stressing the system a little bit? See if we can increase that threshold to 60%. So we were testing at 40% threshold, 40% certainty, spray at the hair fescue if it thinks it's hair fescue. So we tried that at 60, and we still hit almost 94% of the hair fescue, 93.8%. But we also saw huge efficiency improvements because we were missing a lot more blueberries. We had a lot less false positives by increasing that threshold. So that's great. It works in May, but we already knew it worked in May. It worked in 2024. So the real test was getting it out this fall. And just with weather and personnel timing, we didn't manage to get out until yesterday. So thankfully, my supervisor was available to help me out, and we drove out to Rawdon. We took our sprayer out, we set up our plots, and the image on the right-hand side of the screen is a picture from yesterday. Now, we aren't just using water-sensitive papers anymore. We're using those, but we also have these long sprayer test tracks. So that is a 2x4 that is routed out and has receipt paper inside. And we use dyed water to apply on that. And what that gives us is swath width and swath distance as we're traveling along these plots, so we can get more information on where we're spraying and how much. The other thing I want you to take a look at is the hair fescue in that image. We have brown blueberry plants 2.5 weeks after they were mowed, and we have brown hair fescue. I mean, it's hard for a system to pick out brown on brown. A lot of the commercial systems that are out there in the major cash crops like corn, wheat, soybean, when they're doing this vision-based detection of weeds for spot application, they need that green to be able to pick out weeds. And when I tested this system that's based on neural networks instead, even though it's a very brown color, it's able to pick out a lot of it. Yesterday, we hit 87.5% of the hair fescue targets that we laid out. And our precision, so our efficiency, was the second highest it's been in any test. If we wanted to be able to hit more of that hair fescue this time of year, we could lower that confidence threshold to, let's say, 30%, 25%, and our spray events are going to go up, which means our recall is going to go up. We're going to hit more of that hair fescue, even if it hurts our efficiency and we're spraying more blueberries. In the ideal scenario, we're hitting all of the hair fescue, and then anywhere that we can not spray just blueberries is an efficiency saving. It's with the current state of artificial intelligence, this is never going to be 100% efficient, but what it does is it creates a cost saving. If it's definitely not an area with hair fescue, this system is just going to keep those nozzles closed, and that way you are going to be saving your curb or whatever's in your tank. So next up, we actually have a video that I captured yesterday while Dr. Esau was driving the tractor. We designed this system to work basically at a 20-inch spray distance, so 20 inches from the ground or the canopy, which is standard for these types of spray applications. Due to how bumpy the field was, we had to pick the boom up quite a bit higher. We were more like 35 inches off the ground, and that's just because of the bumps. We didn't want to see the boom dragging into the ground. And in the video, you'll still see it swipe the ground in a few spots because that's just how bumpy it was. But when you watch the video, just so you know, it will work at 20 inches as well. So yeah, this was yesterday in Rawdon, and we can see the nozzles firing as we go over those hair fescue plants. The yellow-green flags are target locations, so we have water-sensitive papers right at those yellow-green flags. You can see my 8-foot-long 2x4s, which have a white flag on one end, so that is where we're measuring with our receipt paper. And you can sort of see the blue dye coming out with those spray applications. As well, the red flags are negative locations. So it's an area of our test track that had no hair fescue. So ideally, that nozzle should stay closed. But as I mentioned with AI, it's a probability game the whole way through. So if it's not quite certain, we have to decide what that threshold for certainty is when we spray. So we did see some false positive applications as well. So I've talked a lot about hair fescue, but we also have this working for goldenrod too. We collected some images in 2024 of a post-emergence field in North River. Took some pictures of goldenrod and wild blueberry plants. Once the leaves grow and green up, to see how we could detect green on green. And on and overall, it does work really well. The AI trained to a very high level of accuracy, and we've tested this with the boom sprayer. The main thing that we're having an issue with the goldenrod is the taller plants. With these cameras, if our object is too close to the lens, that object's out of focus. So with the really tall plants, we're having trouble spraying them right now. Anything that's close to the ground, we're definitely going to get. So there's a couple solutions that we've been thinking of to help make the system work better with goldenrod. The first, the obvious one, is just pick the boom up higher, but then you're going to have issues with drift when your boom's too high. The other thing that we did some testing with a few years ago was actually angling the cameras forward instead of having them straight down. So that way, if your camera angle is kind of pointed at a 45-degree angle, you can pick the weed up before it's directly below that lens. So one, that gives you more processing time, but two, it gives you that greater distance away from the lens, so the weed stays in focus, and then the AI can pick it up properly. And with that, we can hit goldenrod as well. For the next generation of this software, we're looking at doing detecting more than just these two weeds. We're working right now on labeling a bunch of images that have a lot of species that we would typically see for pre-emergent herbicide application. So we have our hair fescue, we have other grasses, we have broadleaf herbaceous leaves, and we're currently labeling those in a manner that not just draws a box, but actually just outlines the shape of that weed exactly, which is really helpful for something like moss that you can't really just put a square box around. Um, so we're hoping next year to be able to actually test this and see, uh, have this work in more species and multiple species with the same algorithm. So rather than just picking the hair fescue algorithm, you can just load this up and whatever's in your tank, apply. Uh, the other thing too is just trying to round this out a bit. We know from a research standpoint that we can hit hair fescue, and if our camera distance is far enough, we can hit goldenrod. Our results are showing that really well, but it's not quite ready to give out to you yet because it's just not polished. When I'm changing that confidence threshold, I'm typing commands into a terminal like I'm running a DOS computer, which I know none of you, except maybe Eve, if he's still in the audience, would enjoy doing. Um, so we're going to get that, with a much simpler system for you where you can press a button or turn a dial and then have the actual physical system a little bit more presentable too. Right now, the cameras are in 3D printed cases, which isn't the most, let's say, professional looking system. It's worked for us. It's kept the cameras dry, but we'd like to actually get this to a point where we can get this out to you and you can start adding this onto your own sprayers very soon. So the other main part of my research is developing some algorithms to help with field scouting using these technologies. Uh, Last year, I mentioned that we had started work on detecting F2 buds with convolutional neural networks, really to try and help Hugh and his team at Perennia out because they have to painstakingly go around and count all these buds in the spring so they can update their blight line and blight blog. Last year, the issue we were having was the F3 and the F4 buds weren't being detected very accurately. And Based on what we saw, it looked like it was just, we didn't have enough training examples. We only had a few hundred labeled examples of F3 and F4 buds. Well, we had more than 1,000 examples of F1 and F2. So what we did over the summer was we labeled another, almost 300 images of buds in various development stages, but really heavily weighted towards F3 and F4 buds. And now we have at least 1,000 labeled examples of each of these four bud stages to help with this algorithm. And we retrained. So now our accuracies are similar for each bud stage, and our overall accuracy increased from 70.9% to 77.5%, which isn't perfect. Now, as far as what the error is looking like, the convolutional neural network does seem to be grabbing all the buds, but it's often misclassifying them by one stage. If it's borderline between F2 and F3 or borderline between F3 and F4, that's where it seems to be making mistakes. So with this level of accuracy, we are getting the buds, but we're going to need kind of an error correction equation to really implement this. So we can run pictures of our stems with this and then correct based on what it sees. And then give an estimate for, what's our percentage F2 to help with our timing of fungicide application, which should make Hugh and his colleagues at Perennia be able to do this a little bit more quickly and a little bit more easily for getting that blight line updated. Finally, I want to talk about just general weed classification. The past couple of years, when I've talked about developing, a weed classification app that we can have on our phones for field scouting, I've noted that the most recent survey that you did in his master's found, more than 200 species of weeds, and for training hair fescue, I had to collect over 4,000 images, which combined to, it's over 1 million images. And I said this last year too, but I would like to graduate at some point. Uh, so I've been trying to figure out some ways to cut down on that data collection time. We talked about repurposing neural networks that are used for facial detection and handwriting recognition because those can train with 5 to 10 images instead of 4,000. And none of them really seem to work for weed species. And a lot of it's due to just the fact that there's so much variability depending on what time of year those pictures are taken. As we have various growth stages of all these plants, their visual appearance is going to change. So we can't really get away with using less images. But I also don't want to collect 1 million images. Some of you might use the iNaturalist Seek app on your phone, which does this. It identifies plant species, animal species, fungi species for us, but it requires us to be online to use it. However, they used to run a competition to try and build the best neural network to do this, which is how they got their app out there. And they published their data set for training. And as it turns out, a lot of the species that we see in blueberry fields are in this data set. So I downloaded that, extracted the species that were in blueberry fields. I went to the weed survey and I picked out all the species that had a relative abundance of more than 1%. So I left out all the outliers and then skipped species that weren't in the weed data set to start with. And it kind of left me with 22 species to work with, just to see if just, having a bunch of these together would work overall and save me some time. And as it turns out, it worked really well. In the worst case scenario, I was seeing 91.3% accuracy, at best 98.6 across 22 different weed species. I trained 3 different sizes of neural networks, so that's just the 3 main sections of the 3 bars are just how many neurons. There's a nano version, a small version, and a medium version that I tried. And after seeing almost 99% accuracy on the small one, I didn't move on to the large and the extra large. As I've mentioned, we typically downsample images. We don't use a full high-resolution image because that would take a lot of processing power. So I tried 3 different processing resolutions, 224 pixels by 224, then 448, then 672. As we increase that pixel resolution, it really helped increase the accuracy as well. Now, the issue with the data set is that it doesn't have every species that was found in the weed survey. However, the iNaturalist website does. People upload their images all the time to get help identifying them. And as it turns out, iNaturalist lets you download as many images as you want, like a lot. 10,000 a day, in fact. They just don't want you to stress out their servers. So I wrote a script, I put it on an old laptop, plugged it in, and just let it go for a couple weeks, and downloaded images of every species that Hugh identified in wild blueberry fields. So the next step, I'm in the middle of organizing these images so I can train them and have a 200 species classifier. I was emailing back and forth with Dr. Scott White about this and what some of the limitations might be. And well, the issue might be that some of the weeds are just too visually similar to one another to be distinguishable. It's going to be hard, let's say, two types of asters are going to look very similar to one another. So that sort of error might cause an issue. In that case, we can probably lump some of these species into broader categories. So we can have, all the asters, maybe two different groups for goldenrod, narrow leaf, and fine leaved, uh, and go from there if we don't see really good accuracy on this 200 species classifier. Overall, though, the errors that we see so far are ones that are fairly predictable. In image number one there, we have poverty oakgrass, and our AI algorithm correctly predicted that it was poverty oakgrass. In image number three, we have woodrush, also correctly identified by our AI algorithm. Now in the middle, we have poverty oakgrass. That's what it was labeled as by the user that uploaded it because they were showing the end of that leaf, right? Just the fine hairs. But in the background, we have those broader green leaves, and that's probably what the algorithm picked out and thought it was woodrush. So the key thing when we're using these algorithms is, when possible, make it as easy for the computer as possible to know what you're actually looking at, because that's an example of where it failed on that specific model that was 98.6% accurate. So I'd just like to take a minute to thank everyone that's helped us with our research over the past number of years. First and foremost, the Producers Association, all of you. Most of this research was funded through you in partnership with the My Tax Accelerate Research Grant. As well, I received some additional funding later on through the NSERC Canada Graduate Scholarship Program. We've also had some funding from the government of Brunswick and the Canadian Agricultural Partnership. Doug Bragg Enterprises has been a long-term supporter of research at our university, and we've had a lot of great work done with them. And most of my field trials have been made possible by the Bragg Lumber Company. They not only allow me to use their fields for testing my precision sprayer, but they also are really helpful with helping me pick out fields. And it saves me a lot of time driving around when my supervisor can call the field manager and say, hey, here's what we need. Do you have a site that we can use? And they come back with some great examples. Uh, I also have to give a shout out to Dr. White for his advice on all of this weed detection stuff. Hugh with help with F2 counts and finding images, and his feedback on the my idea to use the iNaturalist data set for training, as well as all the members of the AMS research team, the Precision Agriculture research team, and the Applied Intelligent Engineering Systems research team. So yeah, thanks so much. And I think we still have a few minutes for questions, right? Yeah, awesome. Yeah, thanks so much for the kind introduction. And thanks for all sticking around for the afternoon for my presentation.